And thank you very much for the opportunity to present here at this wonderful workshop. So the title of my presentation is Quantum Deformed Binary Neural Networks. And this is the outline. So I will start with some motivation around why we are interested in binary neural networks, and also some connection with quantum neural networks. And then I will introduce the main, basically, model we look at and how to perform efficient classical simulations and show some experimental results. So this is work done in collaboration with Max Welling, and it is indeed ongoing work at Qualcomm. So let me start with some motivation. So we have talked about this kind of models throughout this workshop, but just a second.
Sorry to interrupt you. Just seems that your microphone has a kind of strange sound. So.
All right. So let me just try to. Can you hear it better now?
I would say yes, if the other agree. Yeah. Yes.
Yeah.
Thank you.
Okay. So I continue with that. Thank you. So. Yeah, binary neural network. We have binary inputs X and binary weights W, and a layer computes the matrix vector product Wx and takes the sign of it to return an output binary random variable Y. The goal here is to minimize some, say, likelihood of a data D given the weights W over the choice of the weights. So why is the problem interesting? Well, from an application point of view, this is quite interesting because running floating point neural networks is expensive and in terms of power consumption. And so for low power devices such as mobile phones, it is quite appealing to have such models. Furthermore, they also reduce the memory footprint by storing only binary weights. And also from a theoretical point of view, this is quite an interesting problem because, typically we optimize neural networks with the floating point weights, and this can be done efficiently using gradient descent. But here the problem is combinatorial in nature and so harder to tackle. And so for somehow optimizing these networks, a number of techniques have been introduced, in particular estimators of the gradients and stuff like that, which allowed people to achieve pretty good results with these models. So the principled way to tackle this problem is that of probabilistic binary neural networks. So here we replace the deterministic variables, binary variables, with binary random variables, X and W. And so this is, in the picture here, this is represented with these histograms. And then your layer will compute an output probability distribution on the binary random variable Y. The probability distribution of the weights, Q, is parameterized by some learnable parameter theta. And the interpretation of this model is that of a Bayesian neural network within the variational inference framework. In fact, we can see this Q of theta as an approximate posterior of the weights given the data D. And so we would like to minimize the KL divergence, which has a minimum where these two distributions are equal. So the KL divergence between Q and P in the posterior. And this actually can be written easily by Bayes' rule in terms of this new objective, which is the average of the logarithm of the log likelihood. And so practically, this is how you interpret and optimize these models. And you can, in fact, interpret the prediction at inference time as an ensemble average over binary neural networks. So you can sample your Qs, you get different binary neural networks, and then you get an ensemble prediction. And this is actually working quite well in practice. So now I come to some of the main philosophy that I want to apply to this talk, and that other people in this conference are also thinking about. So first of all, we can think about quantum mechanics as a Bayesian theory. And we also know that quantum mechanics is, of course, a fundamental theory of nature. And so what we ask here is, why don't we use quantum mechanics to describe basically machine learning models? So practically this can be done by encoding beliefs of an agent in wave functions and density matrices. And here a cartoon reminds you about the difference between classical probability, where one works with a probability simplex, so for a binary random variable, just this segment, and quantum probabilities, where one works with somehow amplitudes that square to 1. And so the likelihood, in fact, is just given by Born's rule, and one can update beliefs using the quantum version of Bayes' rule, where now one has priors, indeed, on the wave functions. And so this framework can be used, to reason about quantum or classical data as well. And on top of reducing to the classical theory for diagonal density matrices, it also adds, of course, the benefits that we seek for, that are quantum speedups, and therefore quantum machine learning, in fact, is one of the main applications of these near-term quantum devices. So the motivating questions for my talk are as follows. So we would like to replace the probabilities that we saw before in the probabilistic binary neural networks with wave functions. So here the cartoon is to replace this with these block spheres. And so we wonder indeed, what are the good architectures to get good results with these models? And so specifically, we think about three questions here. So the first one is how to implement a binary neural network on a quantum computer. Second one is, can quantum mechanics extend the class of neural networks on a classical computer? And somehow this is, to say we would like to find some models that are quantum and at the same time can be run efficiently on a classical computer, and therefore can be useful also from a classical point of view. It can be benchmarked. And then finally, of course, we would also like to understand what are the advantages of running these models on a quantum computer for classical data. So as a next step, I want to enter the first question. And the first question was about, can we represent a binary neural network on a quantum computer? So we can proceed as follows. We start by looking at classical binary input, say an image here in this cartoon, and we can encode it losslessly in a state of qubits by simply mapping, say, the black pixels to a state of the qubit -1 and the white pixels to the qubit +1. So this forms the input qubits for our quantum algorithm. At the same time, as we also discussed, we would like to replace the classical probabilities with some wave functions. So what we can do is to, in the simplest case, is to just take a separable wave functions of all the weights, and each wave function for, say, the weight wj is now represented in terms of a block sphere with two learnable parameters. So these are the analog, of the learnable probability in the classical case. And so we prepare then some weight qubits whose wave functions are given in terms of these parameters. The next step, we need to replace basically the pre-activations that we compute in a classical neural network with a quantum Hamiltonian. And of course, here we are still in the classical realm, and so we expect this Hamiltonian to be diagonal or classical to some extent. So specifically, if you think about the dot product of binary variables whose values are plus or minus 1, you can convince yourself that then you have n+1 possible values of this pre-activation H, listed here, say, for n odd. And therefore, simply you take a matrix which is diagonal in this basis where we are working on, and it has these pre-activations on its diagonal. It can be written in terms of these two simple Pauli matrices, sigma z, which I denote here as W for the ones that act on the weights, and the X for those that act on the inputs. And then there is an interesting remark, and the interesting remark is that if you look now at the shifted perturbation phi, this number is between 0 and n. And in particular, it can be expanded in its bit expansion using t given by log n+1 bits, and then we can read out the sign of the activation, which is the nonlinearity that we apply in the binary neural networks, by looking at the first bit of phi. Furthermore, we introduce now the unitary operator, which is the exponential of 2 pi I n+1 h plus n over 2, where h is this Hamiltonian here. And trivially, this operator is factorized over j1 to n, and this uj only acts on the jth input n weight. So the next step is to employ a fairly standard quantum algorithm, which is the quantum phase estimation. And now I will review that in this slide. So we first of all create quantum wires, which are these lines, and we initialize, each of these with a certain value of our inputs and weights, and we do that in an alternating fashion for convenience. Then we introduce t, which as discussed before, we set in this example to log n+1. We introduce t ancilla qubits, all in the state 0, and then we act on them with a Hadamard gate. The net effect is simply to produce an equal weight superposition of the ancilla qubit states. So it will be, the input state at this time will be as follows, where X and W just stand for the collection of the inputs and weights. And the next step is to use a controlled evolution of the unitary U introduced before. And specifically, this chunk of the quantum circuit implements the following operation. If the ancilla register is in a state J, then you apply U to the power J to the inputs and weights. As we know, this U is diagonal in this computational basis, and so this simply picks up the phase, which is 2 pi I n+1 phi j. But now the basically goal of the algorithm is to retrieve the sign of h in a specific qubit, and so we are almost done. We realize that by doing an inverse Fourier transform, we can set the state of the ancilla qubits to the value phi, since phi is also a number between 0 and n, integer, in this specific example. So we do that, and we end up with this state. And so we are at this point here. And now simply measuring the first qubit, we get the sign of h, which is actually the output of the classical neural network. So this procedure allows us to implement, in fact, pretty much arbitrary classically binary neural networks on a quantum computer. In general, in the probabilistic setup we discussed in this quantum Bayesian formulation, our input psi will not be, just a state which is given by a B string, like in the previous quantum circuit, but it will be a superposition of those. And so simply what we do then is to, compute the probability that the output is, in a given bit y, by summing over all the possible value of x and w weighted by the probability distribution, and then taking, of course, only the cases where the sign of this, angle perturbation phi is equal to y. So that is the output of the quantum circuit we saw before for generic input psi. And there is, of course, interest in considering smaller value of t, specifically with respect to implementations of quantum hardware. And so what happens in that case is that the output is not, does not decohere, like in this case where it just becomes classical, but it is a coherent superposition of states. And it can be actually interpreted as a soft nonlinearity. So here we see this purple line is the sign of linearity, and corresponds to a maximum value of t called log n plus 1. And then for these other sinusoidal curves, these are approximations of the sign of linearities for a smaller value of t. So it's pretty nice somehow interpretation in terms of neural networks also of the value of the cases where t is smaller than log n plus 1. And we can apply straightforwardly also this algorithm to convolutional layers. So before we imagine the fully connected situation, in a convolutional layer, we simply apply this algorithm patchwise. And in terms of novelty, it's also important to point out that the basic ideas were, are pretty natural, in fact, and they were laid out for the perceptron in this paper by Schultz et al. And our contribution here is the generalization to Bayesian, if you want, quantum neural networks and to the convolutional neural networks. And that's actually important because it will allow us to scale up this model also in the classical case. So now I want to introduce the main somehow insight that we bring forth in the modeling of quantum neural networks, which is the quantum deformation. So we are used to think about classical somehow mechanics, and in particular also classical neural networks, as a particular case of more general quantum mechanics or quantum neural networks in this case. And the difference, is that in the classical case, we work with diagonal and real Hamiltonians. In the quantum case, we work with non-diagonal complex Hamiltonians. And so the point here is that there is a case where, we can take a quantum neural network and take a specific limit, which h bar equals 0, where this degenerates the classical neural network. And so we think that this way of thinking is actually pretty fruitful, and it is in fact the principle of quantum deformations in general. It has been used many times in mathematical physics when you think about deforming classical structures like geometry or integrability. And so it is really a guiding principle in those areas, and we also use this as a guiding principle for us to design quantum neural networks by deforming classical neural networks. So how does this go in practice? Well, so remember that we had this diagonal classical Hamiltonian, which is given, by the sum of these diagonal operators. And simply now we add some parameters, say h bar, and some more general Hamiltonian, which has off-diagonal terms. So that will be now the Hamiltonian we consider in the quantum deformed case. And then we simply apply the same quantum phase estimation circuit that we discussed before, not to that diagonal Hamiltonian, but to this more general Hamiltonian H. So without, recalling too many details of this construction, you can imagine that what is relevant here is the spectrum of H. In fact, the quantum phase estimation is precisely estimating the spectrum of H. And so if you think about e to the IH, this is a unitary, so its spectrum lies on the circle. And then again, we can make sense of the sign of this phase by looking at where this phase is, say, on the top or the bottom of the horizontal axis. So in the general case, we will replace the sum over, the x and w, the inputs and weights, which were the eigenstates of the classical Hamiltonian here. We will replace them with the sum over lambda, which are the eigenstates of the more general Hamiltonian H. And so the layer just defined will compute the output probability that the sign of the eigenvalues phi is a given value y. And the nicety of this construction is that it smoothly, reduces to the classical neural networks when we tune this parameter to 0. So to put things together, we can proceed as follows. We take an input, we encode it in a wave function psi-x in a lossless fashion. And suppose that we are looking at a supervised classification algorithm. So we also have a bunch of labels. And so what we do in this cartoon is that we take, these boxes, which are these quantum phase estimation based layers introduced before. We input psi and some wave function psi w of different weights here. And then we concatenate the outputs like we usually do in a classical neural network and produce an activation wave function psi y. And then we can stack this in a certain number of layers. Here for simplicity, I just do one layer. And at some point we measure the wave function and we spit out probabilities of the, that we interpret as a probability of the class that we want to classify as being 0 or 1. So it's a pretty straightforward protocol and interprets directly the probabilities of this quantum network as the class probability in a natural way. And so the target of the training algorithm is then naturally to minimize the prediction, the cross entropy between the predicted probabilities and the target probabilities. And this minimization will be done over the space of wave functions psi w in analogy to the classical probabilistic framework, where it is the minimization is over the variational parameters of the posterior. So a simple remark, I mean, we have already actually heard a lot about software implementations of quantum circuits and so on, but you can imagine that this is also, one can implement these layers with that software. In fact, we did it ourselves, and these layers, in fact, are trivially differentiable because it's just a combination of unitaries and measurements, and therefore can be implemented, say, in an automatic differentiation framework. And this is actually pretty interesting, also from the point of view of binary neural networks, because it gives a new way to make sense of gradients of the neural networks which have discrete labels, which have, discrete activations and weights. So without using any specific estimator. Okay, so a few words now on the runtime. So the time to compute the quantum phase estimation basically is the time to have, to apply this controlled evolution times the time to apply a single unitary evolution u. And so in the case of the control part, the classical here in blue runtime is exponential with t, while the quantum runtime is linear. In fact, this is the main reason why things like quantum Fourier transform and quantum phase estimation are popular. And also from the point of view of the runtime with respect to the unitary u, we also know that we can implement on a quantum hardware more efficiently, exponentially more efficiently, certain unitary evolutions. And so this is featured in this cartoon. But however, we know also that from the classical point of view, depending on the entanglement structure of your unitary, for example, in the case where it can be captured by tensor networks with finite bond dimension, we can also find pretty efficient algorithms there. And so that will depend indeed on the structure of U. But however, it's pretty disappointing somehow that we need to pay an exponential price in t, even though t, would be basically related to the logarithm of n. So that would mean in that case that this price would be a price which is n times the time of U. So we wonder if you can do better classically, in fact. And the answer is yes. And the framework where we do that is the framework where we have maximum precision, so where we set this number of ancilla qubits equal to the logarithm of n, and so where the layer computes exactly the output probability without any further approximation error. So in that regime, we consider now the simplest case, where the Hamiltonian is not diagonal, but still it's a sum of commuting terms. So, and we also assume that these terms to start, they act locally. So they basically say HI acts only on the ith input X and weight W. So in this sense, the Hamiltonian is a sum of independent and independent classical random variables, since they all commute. And so we can apply, so this is actually written here at the level of the eigenvalues. They can be written as a sum of, random variables. And so we can apply straightforward the central limit theorem to estimate the probability of the pre-activations, even in the general setting where these matrices, are non-diagonal. And so this will be given in terms by Gaussian, where the mean is the average of H and the variance, is basically the variance of H in the state psi. So after this, we know that phi lambda is Gaussian. We can take the sign, and so taking the sign is straightforward. We just need to integrate over. So if the sign is equal to 1, we know we just need to integrate over this positive region to get that. And so we can express the probability of the sign of phi given a certain value in terms of the cumulative distribution function of the normal distribution. So all this is very nice, and in fact allows us to have a very nice algorithm which is very efficient or in complexity. Just need to do a bunch of, basically summations here and here. And in fact, this is also a generalization of previous similar remarks in the case of probabilistic networks to the quantum setting. So armed with these insights, we set out to do some experiments. The first kind of experiment here is the experiment that looks at the quantum phase estimation versus the central limit theorem approximations. So we have two models in this experiment: the probabilistic binary network of the introduction, where we use the central limit theorem approximation, and here we only use classical variables. And we compare that with the quantum binary neural network without any deformation, which we call QBNN, and where we use the quantum phase estimation. So the first kind of check that we did was to train a probabilistic binary neural network, a very fairly simple one, so one hidden layer MLP on MNIST, and we get a certain accuracy, which is not great, but still is just just a reference here. And then we try to transfer the weights on a quantum binary neural network and use the quantum phase estimation and see what's going on. And so these numbers here in parentheses are the number of ancilla qubits in the quantum phase estimation for the hidden and last layer. And so we see actually that we can get to pretty good accuracy, so 1% loss, even if we have more or less these numbers. And so this is a pretty nice indication that it might be actually useful to use the quantum phase estimation in practice. However, when we try to train from scratch using a quantum phase estimation, instead of using a CLT approximation for the quantum binary neural networks, we get actually not great results. So it turns out that backpropagating through these quantum circuits makes the learning problem actually pretty difficult, and some numerical errors and stuff like that enter. And so it's not straightforward. And so we abandoned actually that line of thought, and we come now to a more interesting experiment where we use the central limit theorem in the context of the quantum Hamiltonians, and in particular in the simple context that we discussed before as proof of principle somehow of these ideas. So we consider now a simple deformation where instead of acting with xj, which just measures the value of the jth input spin, we add a g times f, where f is the spin flip, so which flips that spin. And so we take also this g to be uniform across, spatially, if you want, across the neurons it is acting on. So we performed experiments again on MNIST. So I just want to stress here that here we work with full resolution, thanks to the classical efficient algorithms in this case. And we use a backbone for the quantum deformation, which is given by the following architecture, which is a VGG-like architecture with 2 convolutional layers, C, with filter size 3 and stride 2, just for doing the sampling, and then we pipe 2 fully connected layers, so with these sizes. So the good news is that we managed to train smoothly this quantum deformed neural network using the CRT approximation, and we get a pretty good accuracy for this task. In fact, for the binary case, and this architecture is quite good. And interestingly, what I find fascinating is that the stochastic gradient descent, starting from some random value of g, settle down on some non-zero value of g. So it means that it is actually finding some deformation of the classical layer, which are useful for learning in this task. However, if you compare with the classical baseline, which is the case without this deformation and trained as best as we can, we actually get only a small improvement, which is order even smaller than 1% for this task. So it's a bit unclear, indeed, how it compares with classical baselines in general, but still it's on par, if not slightly better. What we think is actually quite interesting, though, is that we think it is actually a big improvement with respect to previous quantum neural networks, which had, here I just list two papers. There are, of course, many of those which tried to use variational quantum circuits for classical data. And the punchline is that the architectures used there did not allow, basically efficient classical simulation. In fact, they also used some tensor network architecture, but still they could not, get to anything close to full resolution MNIST. And so we think this is actually a pretty interesting development in this field, where we now can have some knobs which allows us to, test things on large scale, real world data scale size for quantum neural networks. And as I said, the reason is that we have these classical simulations in this case, and so this is very fast. So this is nice, and this is quite encouraging. And of course, what we would like to do, and now I come towards my outlook, I understand I'm already a couple of minutes late, is to look at more complicated Hamiltonians. So
Roberto, can you just check your microphone again, because it's going on and off a bit.
Oh, sorry, maybe it's related to my connection. Can you hear me well?
This is better.
Okay, so I just speak closer to the computer.
Oh, this is worse.
All right. Now?
Yeah, this is good.
All right, so I'll try not to move. Anyway, I'm basically done, and I just wanted to point out how do we extend these things now to more complicated and in principle indeed entangling Hamiltonians, which is the real interesting case here, and where we expect to see some quantum advantage. So there are several ideas that we are exploring, and here I'm just sketching one. So we consider conjugating the classical Hamiltonian with some unitary evolution operator D, in such a way that the Hamiltonian is still a sum of commuting quantities, but these now are not localized on a single site I, but can be spread out according to the spreading given by this D. And so in this case, if it happens that the correlations that are induced by this D guy on the operators in the wave function, input wave function psi, are such that the connected correlation functions, tend to 0 as these insertions point are far apart, then we can apply still the central limit theorem in the case of weakly dependent random variables. And so pretty nicely, the computation boils down again to just computing this mean and variance. And so a promising direction here is in fact where we use a quantum circuit, which is a small depth quantum circuit. And as we also discussed, we heard this morning in the talk by Jens, it's actually very convenient to do simulations of these systems using matrix product states. So here I'm a bit, lacking maybe explanations. I hope you were there in the talk by Jens, but roughly speaking, these boxes are the separable wave function of the input, and these other boxes are the unitaries of the make up D. And then, you can imagine contracting these things, and you can imagine having a representation, graphical representation like that. And then there is a whole literature on matrix product states that allow you to compute efficiently this mu and sigma square in line time. So this is a pretty interesting direction. And but I do not have numerical results, unfortunately, at the moment with this. So this is left for future work. So I come to the conclusions. So we introduced new quantum Bayesian binary models, and we also showed how we can efficiently simulate classically some simple examples of those. And importantly, I think for the first time, we showed how we can train a quantum neural network on real world data, and we got a good performance. So ultimately, I think that these quantum deformed binary networks are a promising class of new layers, even classically. In fact, you can think that if you can simulate these models classically, they can also bring some advantage in terms of representation and in terms of, say, number of layers that you need in your neural network to build up correlations. And so the outlook, like many of you in this conference, we would like to understand better how quantum mechanics can build good machine learning models. We think that this direction is a promising one. As I mentioned, there are these extensions to entangling layers where tensor networks, exactly sortable models are being explored. There is also, of course, the potential of using a quantum computer to have it speed up to compute the quantum phase estimation. And as the MNIST task is notoriously simple for neural networks, we are also exploring Cypher-10 and ImageNet benchmarks. And it is proving crucial here actually to use a form of batch norm, even for the classical baselines. And so we're doing some works to extend this to the quantum case, use pooling and so on and so forth. And ultimately, I think also it will be interesting to explore applications to quantum data and built-in symmetries, which are pretty natural from the Hamiltonian point of view. So with that, I would like to thank you for your attention.
Thank you very much. Let's see whether we have some questions. Florian.
Yeah, just a very simple question. So you got this improved performance when you added the spin flip operator, a little g times capital F, right?
Yes.
Can I relate that somehow to dropout techniques, like adding noise helps, or there's no relation?
Well, you're right. This is a kind of noise that flips the spin. And it is true that there might be a way to reformulate this classically, but still I think it's a distinct mechanism. Perhaps the philosophy is similar, but it's a distinct mechanism. So I think it's quite interesting to see that, we can have some quantum-inspired tricks or quantum tricks, that still can give some meaningful classical results.
That's very nice. Okay.
Thank you.
Ricardo?
Yeah, just probably the simplest quantum approach to binary neural networks is just to think about quantum annealing, in a straightforward manner. So it's also kind of a quantum deformation, right? So
exactly.
So did you compare with that?
No, but I appreciate it. That is actually very interesting. I mean, from our point of view, we would like to understand something, somehow some inspiration or some quantum ideas in the classical world. So that will be our goal. So we would have to do some simulated quantum annealing, which is something we can do. But I would assume that if you do simulated quantum annealing or maybe even quantum annealing, you do not get a good performance on say classifying images, right?
No, you do. I think you do, but
you do.
Yeah.
Okay, so this is definitely something that I will have to look into more. But thanks for pointing.
It's very demanding from a computational point of view.
Exactly. So that is indeed one of the reasons why we try to use these deformations from classical neural networks that we can efficiently simulate to actually benchmark these things, because otherwise it's very difficult to understand what works well and what doesn't.
Yeah, I understand. Thank you.
Thank
So
you.
I also have a question. So what is not completely clear from your talk to me is whether your message is that using this approach gives better functionality for software solutions for neural networks, so enhanced performance, or is this also for circuits?
Yeah. So from my talk, the message was that use a new somehow modeling paradigm for circuits, and this modeling paradigm relies on basically years of research in classical neural networks to figure out what are good inductive biases like convolutional structure, stuff like that. And so, but it adds on top of that, the possibility of deforming and having the spin flips and things like that, which ultimately we hope would result, in using entanglement to model correlations and allow one to have a shallower network. So I think it's actually similar to somehow the findings you also found in your quantum Bondesan machine, right? That adding some deformations, you can actually have a better result if you keep the same number of layers. Of course, if you increase the number of layers in a classical case, you might also do well, but this is a separate, I guess, question. So yeah, to summarize, we are thinking about quantum circuits, but we would like to, learn something also from the classical world and use this quantum deformation also from a classical point of view as modeling paradigms. We are not quite there. I guess that indeed the dropout and things like that are very good competitors, and I don't know if you ever manage, but still, I think the perspective from quantum circuits remains. These are interesting models, in my opinion, that we could use, on quantum computers to get good results for classical data.
Excellent. Okay, thank you very much. I think there's one more question from Peter.
Hi, Roberto. Did you run anything on a real quantum computer?
No, thank you for the question. Unfortunately, not. We would love to do that, but no. For the moment, we're just benchmarking classically, so that's also why it is taking time to find good primitives to do that. But yeah, that is certainly something we would love to.
Sure. Thank you.
Thank you.